Hello everyone, and thank you for joining us today. My name is Samantha Hull, and I'm a licensing manager at NASA's Armstrong Flight Research Center. I will be your host for this NASA Technology Transfer Program webinar on synthetic Schlieren techniques for flight testing. Our presenters today are Dan Banks, Ed Herring, and J.T. Hynek. Dan Banks is a senior research engineer at the NASA Armstrong Flight Research Center at Edwards Air Force Base, California. He has over 41 years of service at NASA, has authored over 60 formal publications, holds 3 patents, plus 1 pending, is an associate fellow of the AIAA, and was the recipient of the NASA Distinguished Service Medal. Mr. Edward Herring is an aerospace engineer at the NASA Armstrong Flight Research Center in the Research Aerodynamics and Propulsion branch. He has worked at NASA Armstrong for over 36 years, has authored over 50 publications and 4 patents, and has received the NASA Exceptional Achievement and Exceptional Service Medals. He has been the technical lead for many supersonic projects in the areas of sonic boom research, in-flight Schlieren photography, air data calibration, including RBSM, and the use of innovative pilot displays, GPS, and ground-based radar in-flight research. Mr. J.T. Hynek is the lead for the Imaging Instrumentation Group at the Experimental Aerophysics Branch at NASA Ames Research Center. In his 30-year career, his aeronautics test technique portfolio includes particle image velocimetry, thermography for transition detection, photogrammetry, and Schlieren shadowgraph imaging. He has received the NASA Exceptional Engineering Medal, holds 4 patents, and received the 2019 AIAA Ground Test Award. NASA's patented and patent-pending image processing technologies are new and innovative techniques that capture images of shockwaves created by supersonic aircraft. Researchers are using the techniques featured today to study shockwaves as part of the effort to make sonic booms quieter and to open the possibility of overland supersonic flight. Following today's presentation on the technologies, I will be giving a short presentation on how NASA licenses technology to outside organizations. Before we get started, I'd like to point out that your microphones will be muted throughout this presentation. So if you have any questions, please type them into the chat box, and we will answer them during the Q&A session at the end. So, at this point, I'm going to turn it over to Dan Banks to begin the technical presentation. Dan?
Okay, thank you, Samantha. Thank you for joining us today for this webinar on synthetic Schlieren techniques for flight testing. After a brief introduction and some background, we will discuss the 2 methods, Optical and Airboss, then talk about data processing, current and near-term applications, and finish with a summary. Next slide, please. The development of these flight test techniques was sponsored by the NASA Commercial Supersonic Technology Project. The motivation was the desire to develop a Schlieren or similar system to visualize shock waves on full-scale supersonic aircraft in flight. The primary driver was to be able to validate and refine the shock modeling and also propagation for low-boom designs like the X-59 Low Boom Flight Demo, or LBFD. A full-scale Schlieren type image allows you to potentially get actual fluid dynamics instead of CFD. It shows what's really happening. So if and when the predictive tools for modeling the LBFD or other aircraft are off, we have the ability to go in and look and see what's different from predictions instead of just guessing. There's been some evidence that full-scale flight aircraft may generate more shock waves than are predicted at certain locations and conditions. An additional motivation was to be able to investigate this phenomenon. The picture on the lower left shows a laminar flow test article that we tested several years ago. There was evidence of a previously unpredicted disturbance on the test article. The bottom center image is an IR image of that test article during the supersonic flight. You can see these unknown shocks on the wing platform as flown underneath our F-15B test bed aircraft. We couldn't figure out where these were coming from. Although not shown here, a relatively recent Airboss image does show these extra shocks emanating from the lower surface of that F-15. The shocks didn't match, again, any CFD predictions or wind tunnel tests, and a similar situation also occurs on the T-38 four-body shown in the lower right image. The inset of the image shows the CFD prediction, and the overall image shows an Airboss image. And the Airboss image shows many more four-body shocks, again, that weren't predicted. Next slide, please. Schlieren comes from the German word for streak. It is a method of visualizing density gradients. A classical Schlieren system, usually found in high-speed wind tunnels, use a setup of very high-quality optics and lights. The diagram on the left shows a typical classical Schlieren setup for a wind tunnel using lenses, although quite often mirrors are used instead. The light is collimated and sent through the test section and then refocused on the opposite side. A cutoff is placed at the focus, and the resultant image is captured or projected. It's important to note that the cutoff can be oriented vertically or horizontally. Those are the typical two orientations, and you'll see that alluded to later. The gradients are imaged perpendicular to that knife edge. And the image on the right shows a typical Schlieren image from a wind tunnel system. The method requires very precise, expensive optics and was actually derived from a technique to test optics called streak photography, hence the name Schlieren. But the takeaway here is this would be prohibitively difficult, if not outright impossible, to implement in flight. Next slide, please. Background-oriented Schlieren is considered not a real Schlieren, but a synthetic Schlieren technique. The diagram on the left shows a general Boss application where a speckled or textured background is imaged behind the target. The figure on the right shows a typical process result from a Boss system in a wind tunnel. A similar scenario takes place in flight, except we are using the ground, sun, or other natural object for the background. The shock waves or other phenomena create a density gradient, which cause the light rays to deflect, much like that of a spoon in a glass of water, because they change the index of refraction, but only much more subtle than the spoon, and the flow structures are then revealed by the apparent shifting of the objects in the background. So with Boss, the real magic happens in the image processing on the ground. So the setup is far simpler and a much better situation for flight tests. Next slide, please. Just talk briefly about the image processing. There is a significant density change across the shock wave, and these density changes in turn cause a change in the index of refraction. Although not shown, the relationship between index of refraction and density is given by the Gladstone-Dale relationship. The Boss image is a contour plot of these measured distortions caused by the refractive index gradient. These image processing equations are fairly complex, but a short version is that the images with the shock waves are compared to the undistorted reference images, and the pixel movement is recorded. There are two image processing methods currently used, one based on the cross-correlation, like what's used in PIV, particle imaging blussimetry, and a relatively newer one based on the optical flow algorithms. This will all be discussed in more detail a little bit later. The video clip on the right shows the apparent shifting of the background due to the shock waves. This is the nose of the T-38, and you can see the background scintillating as the shock waves pass over in this case, it's the desert background. So these all can be seen visually, and this is what's happening in the image process, and we're actually pulling out these details. And you'll see this a little bit later. JT will talk about it a little bit more. So why don't we go ahead, go on to the next slide, please. So we've developed two related methods of in-flight background-oriented Schlieren. The first method is called background-oriented Schlieren using special objects, or BOSCO, which for short, which uses the ground-to-air sensors currently and the sun as the background. An example image is shown on the right. The method is currently implemented in the ground-to-air mode, but we are working on developing an air-to-air BOSCO capability. The method is capable of imaging a side view in a 1G level flight. And this is important because it's the downward propagating part of the shock wave that eventually reaches the ground and creates the sonic boom that we seek to mitigate. However, a limitation to this method is that you're limited to the 1/2 degree field of view of the sun, although by using multiple sensors, a mosaic can be created for a wider effective field of view to mitigate this limitation. The second method, called air-to-air background-oriented Schlieren, or Airboss, as currently implemented, is a downward-looking from an observer aircraft at the desert vegetation, ocean speckles, or other possible backgrounds. An example image is also shown on the right. It has a very wide field of view and can obtain very detailed results. To get other than the top-down aspect or profile view currently requires aggressive maneuvering, like the so-called knife edge maneuver from the aircraft. This works really well for fighters, but probably not so much for aircraft, certainly not the X-59. However, a new development of Airboss is using simultaneous referencing, or we call it Airboss SR, which would allow acquisition during formation flight and oblique viewing. This could mitigate or possibly even eliminate that limitation. I'm now going to turn it over to Ed, who will give you some brief history and then describe the Bosco technique. Ed, next slide. Ed.
Thanks, Dan. 27 years ago in 1993, NASA Langley scientist Leonard Weinstein developed a ground-to-air sun edge Schlieren system showed here in the center drawing. Basically, he masked out all but a slit of the sun edge. The sun edge acts as both a light source and a cutoff. You can see the shock waves distort the edge of the sun, as well as making the sunspots twinkle. As the aircraft eclipses the sun, an 8mm street camera is used to combine the edge distortions and produce the image like the one on the left. An improved digital equivalent was produced 20 years later using hardware developed by Metrolaser Incorporated and processed with NASA Armstrong algorithms. A digital mask is applied to the image after the flight. While this is not background-oriented Schlieren, it was nonetheless an important intermediate step. All of these images were taken from the ground of full-scale aircraft in supersonic flight. Distortions of the sunspots in the interior of the sun gave us the idea to use the entire solar disk for Schlieren images, resulting in the Bosco technique. Next slide, please. Here we look closer at the ground-to-air Bosco concept. We use the sun with a narrow-band optical filter as the background. We use both a hydrogen alpha and calcium K filter. Hydrogen alpha works a little better. Advantages of this method are low cost and the ability to view the shocks from the side. These are the shocks that hit the ground and create the sonic booms that we seek to reduce. Next slide, please. Here's the hydrogen alpha filter. It provides a spectral background of the sun that is static on the order of about 20 minutes. The aircraft eclipses the sun in a fraction of a second, and high frame rate video captures the distortions of the speckles by the shock waves and vortices. Next slide, please. This is the hardware used in the ground-to-air tests. We have a telescope, solar filter, a high frame rate camera, about 1,000 frames per second, and a way to track the sun and trigger and record the images. This equipment is generally used for astronomy work. Next slide, please. Getting the aircraft to eclipse the camera was not an easy feat at first. The region that the aircraft had to hit was about 100 foot wide. Knowledge of the solar position with time and camera location are needed, as well as the aircraft location using GPS. Flying along the path of upcoming waypoints greatly minimized the required timing accuracy of the eclipse. Next slide, please. The images of the shocks directly below the aircraft are the most interesting as these reach the ground. For this type of image with a ground camera, the aircraft must be banked to the sun elevation angle as shown in these images, 60 degrees. The limitation of the half-degree field of view for an individual camera is lifted by using multiple imagers with slightly overlapping fields of view. The image on the right uses 3 imagers to give a mosaic of a wider flow field. Airboss will put these optics into a second aircraft, allowing the test aircraft to remain wings level during sunrise or sunset imagery, and also giving much more detailed images. Now I'll turn over the presentation to J.T. Heineck for a discussion about Airboss.
Thanks, Ed. So as Dan had alluded to earlier, Airboss is now looking in the opposite direction as the Airboss Go technique. We fly an aircraft, as you can see on the diagram on the left. It looks down at a suitable landscape that can mimic the speckled backgrounds that we use in ground testing, such as in wind tunnels. Here the diagrams are showing our slow-moving observer aircraft with cameras looking down at the flora of the desert. The data acquired is a sequence of images of a faster-flying aircraft through the field of view, making certain that at least several frames prior to the plane entering the field of view are recorded. Those empty frames serve as our reference images. The Black Mountain supersonic corridor, where the flight tests for the imagery we show were produced, is populated with these creosote bushes, which is shown in the lower left corner there. They survive the arid climate in part by spreading natural herbicide to keep away competitors. The result, for our purposes, is nearly ideal as views from altitude shows. To further improve the imagery, we use a long-pass optical filter that darkens the bushes, thus increasing the contrast against the light gray soil and dried grass. Many landscapes, actually, including sun glint off a large body of water, can serve as a suitable background. Next slide, please. So operationally, we fly a King Air. It's a B200 Super King Air, but this one is fitted with a native view window port. We can fit 3 high-speed digital cameras to look straight down, so that we have both redundancy and the ability to choose a couple of different fields of view widths. Each camera can record at least 200 images of the fast-flying aircraft below. The data we show is of a T-38, seen on the right, which is operated and piloted by the Air Force Test Pilot School. The flight plan in the lower diagram shows how each aircraft flies along a common line, but independent loops. And each aircraft is using a GPS to guide them on that line. Each aircraft is also monitored in the control room via radar, so that the controllers can offer guidance to the T-38 pilots to time their pass. Now, we as operators in the back of the King Air are watching this visually, and we simply trigger when we see them enter into our frame, and then save the imagery for later processing. Next slide, please. So let's look at this data here. So this is the knife edge maneuver that Dan alluded to earlier, and this happens to be probably one of our best passes over the perfect background. The sequence shows the enhanced contrast given by the filter. We then fly selfies that have the best pilots in the world to fly this. But one should see the shock waves scintillating the shrubs, and as we saw in Ed's Bosco sequence earlier, here the frames are registered to the data frames, and the image processing algorithm is applied. We then see the individual frames processed and rendered as contour plots of deflection. Those individual solutions are then aligned to the aircraft and averaged to give us the very high spatial resolution of the final image, as you see here. The image of the target itself is cut from the raw data and then pasted over the noise caused by the blockage of the background to show where the shocks are emanating from on the features of the aircraft. Next slide, please. Here's another example, but this time with 2 T-38s flying in formation, one wingspan apart, to show us how the bow shock of the trailing aircraft interacts with the tail shock of the lead aircraft. The distortion of the bow shock in this data set challenged the CFD community to replicate the physics. Additionally, we see the shocks that from the trailing aircraft reflect off the lead aircraft's exhaust plume. This has not been observed in wind tunnel testing and has very important implications for the X-59 wake signature. This imagery went viral when NASA Armstrong publicly released it last year, capping off with the journal Nature publishing it in the issue of Top Science Images of 2019. Next slide, please. So Dan talked about the modification of our original Airboss technique by calling it Airboss SR, or Simultaneous Referencing. So clearly we cannot fly our King Air at the nominal cruise altitude of 50,000 feet, where the X-59 will be flying. We will need another aircraft to fly in formation with the X-59, which means that the best way to acquire it is by recording the reference simultaneously with the data imagery. by using two cameras with lateral offset pointing angles, such that the forward-pointing camera records the background imagery without the aircraft, and the aft-pointing camera is composed with the target aircraft. The offset in space allows for the target to enter the portion of the desert recorded earlier by the forward camera. Data reduction would be sequential instead of using a single image or a single batch of images against all of the data images. This technique does not require high-speed cameras, so new super high-resolution cameras can be used. With BOSS, the more pixels, the merrier. The technique is third in this portfolio, third patent, I should say, in this portfolio. Next slide. So this is a somewhat more simplified diagram of what I was alluding to. And as you could see in two different times from T0 to T1, in T0 you acquire a reference at T1, at T0, and a data image at T0. At T1, the reference from T0 serves as the reference for the data image from T0, and so on and so on. Next, please. So to illustrate the efficacy of the SR technique, we just looked at some legacy data where we could essentially treat the sequence of images that we took as if the data were going to be processed sequentially. In this original process data set, each image is processed with 10 reference images as a way of reducing the noise of every individual image. And then all of those solutions are then aligned to the aircraft based on tracking its distance and movement within frame to frame, and then aligned in simple average. The Bruce is very clean, very detailed image. Next, please. We processed with the exact same set of data images. However, instead of using a single batch of 10 images to serve as reference, the empty frame, we decided let's process this as if they were all flying together. So as the aircraft passed through the field of view, we chose 10 earlier images from that sequence to act as the references. It shows that the processing does not degrade one bit the quality of the data of the actual target image. This ghost image was just simply a byproduct of the simulation, and when we set up to do the SR data acquisition technique, we'll make sure that we don't have any overlap of those of the two images. Next, please. So I'd like to revisit the image processing that Dan introduced earlier, because clearly this is a very huge part of the technology. The algorithms we originally were originally developed for another measurement technique, particle image velocimetry, or 2D cross-correlation emerged as sort of a default technology. As a result, there are many commercial programs available in which this image processing technique is worked out and is statistically very sound. Recently, though, it has been found that optical flow codes that were developed for computer vision applications very nicely adapted to loss processing, since it is fundamentally a different problem than what PIV poses. The optical flow solutions are at each pixel in the original image, whereas cross-correlation solutions use interrogation windows. Therefore, it's a small subsection of pixels that are compared between the reference and the data image. And since it is a window of pixels, generally processed with a grid of nodes, where that node grid is 75%, or where the interrogation windows generally overlap by 75%. So the grid becomes the resolution of the final data product, and thus inevitably is going to be much lower in resolution. So currently, both at AFRC and at ARC, we use in-house developed software packages that are very low level, command line, but they are very computationally efficient as a result. We have done several extra flow utility, workflow utilities that allow us to do automatic registration, to reference the data images, multi-referencing processing, as well as target tracking so that we can align the solutions. Next slide, please. So this is a quick comparison between the cross-correlation method and the optical flow method. It's pretty obvious that when you look at the area around the canopy and the nose, there's quite a bit more detail rendered, as well as a more accurate rendering of the flow over the wings and the wingtips. You can definitely see much more detail there as well. So our default has become the optical flow algorithms for when we do our processing. Next slide. But there's also a huge advantage to BOSS output such that the same data set can be rendered in any manner such that we can replicate the horizontal knife edge, the vertical knife edge, and essentially a shadowgraphy with the absolute magnitude. Depending on how one plots the data, whether you look at the deflections in the vertical direction or horizontal direction, different flow features can be brought to bear, or brought out, I should say. And most notably in the center, when we plotted out the vertical knife edge type image, we found that the tip vortices show very clearly. So since the tip vortices are a product of all aircraft lift, we can definitely see the tip vortex structures from subsonic aircraft and helicopters, of course, as well. That's a very important point to make, I think. Next slide, please. Okay, I'll hand it over to Dan to bring us home.
Okay, yeah, thanks, JT. As mentioned previously, the LBFD or X-59 has been the main focus of this development. We are currently working with the Navy to develop an air-to-air BOSS system using their Navy ATIMS, so-called ATIMS 5 pod. The pod was originally designed to house different types of sensors, but looked like a really good match for our proposed operations. We're also developing an oblique viewing Airboss SR system that would also be incorporated into the same ATIMS 5 pod. We still need to validate the oblique viewing for both passive, that's like a desert type of background, and a reflective, that would be the ocean glint type background. Finally, we are researching methods to obtain quantitative Schlieren. This is the holy grail of these systems. The ultimate goal here would be to obtain local pressure, although initially local density or density ratio would be a more direct and easier quantity probably to obtain. We will need to add a probing and a CFD, and a CFD would probably need ray tracing to close the loop, and probably also need tomographic imaging, that is, taking several slices at different angles to recreate the 3D shockwave field. And with the ATIMS 5 pod, it's a turreted pod, so we should be able to maneuver around and possibly get several of these slices for the tomographic imaging. Next slide, please. So in summary, the background-oriented Schlieren-based flight test methods have been successfully developed for both the ground-to-air and air-to-air imaging of supersonic aircraft. Two processing techniques have been used to process the BOSS flight images, the traditional cross-correlation methods, and more recently, the optical flow methods. Hardware and software development have thus far been targeted to support the X-59 low-boom flight demo, but the techniques are applicable to a much wider range of aircraft and flight conditions. Applications to high-speed flow, such as you've seen today, shockwaves, has been shown, but it is also suitable for applications imaging of vortices at both the high and low speeds and any other flow phenomena that would create a density gradient and thus the changes of index of refraction. We're continuing our research and development of the technique with the ultimate goal of the quantification to obtain a local pressure ratio, or again, at least density or density ratio. So thank you for your attention today, and we'd be happy to field any questions.